Hey everybody, this is Dr. Bricker here with Chapter 6. I want to go through a little review of what we did in the beginning of Chapter 6 and then talk about a little bit more with Chapter 6 and then touch on the lab that concerns centripetal force and circular motion. So we saw this before, that the radial acceleration, or the acceleration towards the center, in other words, along the radius, for circular motion is equal to v squared over r. So v is the speed, and r here is the radius of the circle. This comes out in meters per second squared, just like we've seen before. In conjunction with this, we have that the speed is the distance around a circle, 2 pi r, divided by the amount of time it takes to go around a circle, which is the period. So be careful, this big T stands for period, not tension. Okay? So uniform circular motion means constant speed, but we do have an acceleration because the direction keeps changing. So sometimes you can use this equation along with this equation and use them together to solve for the radial acceleration. Actually, maybe I'll do that. So the radial acceleration, v squared over r, but v is 2 pi r over the period. So that's the v squared part. Right? I'm just taking this and plugging it in here for v, and then divided by the period. Don't forget to square that, and then we still have this r left over. So I've got 1 over r here. Okay, so when you do a little bit of math here, things will cancel out. You get 4 pi squared r over the period squared. So that's another way of writing the radial acceleration, and I'll do that here. So 4 pi squared r squared over r just gives you 1r, and then divided by the period squared. And if you want to write that in terms of the frequency, you could do it like this: 4 pi squared r frequency squared. So just another way of writing the radial acceleration. Okay, so that was the beginning of when we start talking about Chapter 6. This actually comes from one section of Chapter 3. So if we have an acceleration towards the center, we have to have a net force towards the center. That's what the remaining part of the chapter deals with. We're just going to be searching for the force towards the center. So let's take a look at that. Okay, so this is where we left off last time. This is slide 26 of the Chapter 6 notes. Well, it's 26 for me. It might be something different for you, slightly. So in this example, an audio CD has a diameter of 120 millimeters, spins at a rate of 540 RPMs. So the RPM stands for revolutions per minute. When a CD is spinning at its maximum rate, how much time is required for 1 revolution? Okay, so we know the diameter. Be careful, we don't know the radius. Well, we can easily figure it out. And we have this number 540 revolutions per minute. We'll have to see what that actually means. And then the second part here, if a speck of dust rides on the outside edge of the disk, how fast is it moving? So in other words, what's its speed? And then also, what's its acceleration? Okay, so before we get started, as it says here, we need to do some unit conversions. So the diameter is 120 millimeters. So divide that by 1,000, because there's 1,000 millimeters in a meter, you get 0.12 meters. So the radius is half that, so 0.06. Now, when you see something in revolutions per minute, that is the frequency. It's just not the frequency in SI units. We need revolutions per second, or oscillations per second, whatever it is. So 540 RPM, that's good, but it's just not in SI units. So that's what's happening down here at the lower part of the screen. You see 540 revolutions per minute. Let's turn it into revolutions per second to put it into SI units. So revolutions per minute, 1 minute 60 seconds. The minutes part cancels out, and then we're left with revolutions per second. So 9 revolutions per second. You can write it like this if you want to. This just means seconds to the -1. Or you could even write it as 9 hertz. So you just need to know what this means. Revolutions per minute, whenever you see revolutions per minute, that's frequency, just not in SI units. We need it to be in SI units to work with it. Okay? So let's see. We're trying to figure out how much time is required for 1 revolution. Okay, so we know the frequency. We know it's 9 revolutions per second. We want to know how much time just for 1 revolution. That's what the period is. So 1 over the frequency is the period. and that's what you see here. So the period 1 over the frequency, 0.11. So just be careful, periods in seconds, frequencies in 1 over seconds, or in other words, hertz. Okay. The next part here is we want to figure out how fast it's moving. Lots of different ways of doing this one. Now, if you wanted to, you could do 2 pi r divided by the period. That would be fine. Here we're just using 2 pi r and then times the frequency, because the frequency is 1 over the period. Okay, so put everything together, 3.4 meters per second. And then we want to figure out the acceleration. We'll use the radial acceleration formula that we saw. Lots of ways of doing this one as well. Here it's 2 pi f, that part squared, that's the speed squared, and then times the radius. I broke it down already, squaring everything in this when I showed you the handwritten part. So 190 meters per second squared. So really, really big, but if you ever saw a CD spin, it's going really quickly. Okay? As it says here. If you've ever watched the CD spin, you know it takes much less than a second to go around. So it's going really fast. There's a big force towards the center. Okay? Great. Let's continue. Hard drive rotates at 720 RPM. Okay, so immediately in your head, this is the frequency, just not in SI units. The disk has a diameter of 13 centimeters. What is the speed 6 centimeters from the center axle? What is the acceleration? So really similar to what we just did. Okay, so let me attempt to write on the actual screen here. So frequency, we just want this to be in SI units, remember. 7,200 revolutions per minute. And then we have 1 minute, 60 seconds. The minutes cancel out. And then you end up with the frequency. It looks like it's 12 here. So 12 revolutions per second. And then that's in SI units. That's good. So we want to know what is the speed, 6 centimeters from the center axle. Okay, good. So we know the diameter is actually 13 centimeters. So the speed that we're talking about is not on the edge. It's 6 centimeters from the center axle, right? The radius here of the entire hard disk that's rotating, it's the diameter is 0.13 meters, so this is 0.065 meters. Let me use a big R for this, actually. That's the actual radius of the hard disk, the size of it. We want to know a speed that's not on the edge, right? We want to know how fast are we going when we're out here at 0.06 meters. So similar to the last problem, just be careful on this one. They give you the size of the disk. We don't want to know the speed on the edge. We want to know the speed somewhere else, a little bit in from the edge of the disk. Same idea here, though. The speed, we can get this like we did before. This will be 2 pi r times f. This is the f here, the frequency in SI units. Now the r that we're talking about is this one. Okay, so put those numbers together, you'll get the speed. The speed depends on where you're at. So if you're closer to the edge, you're going faster. If you're closer to the axis of rotation, you're going slower. The acceleration, though, we can get this way. V squared over r. Right? If you get V from the first part, from this part here, I'll just call this the first part, you can use that V here and then use the r that you have there, okay, to get the acceleration. Okay, so slightly different way of doing it. You could have done it the exact same way as before. Just keep in mind, this is the r that we're talking about. Okay, let's continue on. So dynamics of uniform circular motion. Uniform, again, just means constant speed. Now, if you have an acceleration, you have to have a net force. So many of these problems that we'll use will start off the same way we did before. Net force, ma, it's just a special kind of a. It's radial acceleration. And then that's equal to mv squared over r, putting in this relationship right there. And then the search for the force towards the center commences. Okay? Okay, so this, what you're about to see, is a video from the authors of the book, and we're going to take a look at this idea of force towards the center. So let me play this. Hopefully you can hear it okay. Whoops.
Here I have a circle with a segment of the circle removed, and I'll roll the ball in a circle like so. Now the question is, which can will the ball hit when it exits the circle? Will it roll around to hit the yellow can? Will it continue in a straight line to hit the white can? Or will it continue in a circular path to hit the green can?
Okay, so if there's no force towards the center, which there, well, let me back up a minute. When it's going around here, it's going in a circle because there's the normal force towards the center. That's what allows it to actually go in a circle. So once it leaves this constrained path, here there's no force towards the center. It's just going to keep on going the same way that it would normally go, right? It's going to just continue in that path. Okay, so let's see, straight line. Okay.
All right, let's roll the ball to find out what happens. So as you can see, it hits the white can. While the ball was in the circle was keeping the ball in a circular path. Once the ball left the circle, there was nothing to act on the ball to keep it in a circular path, and the ball wanted to continue going in a straight line. Here I have a circle.
Whoops. Great, so as long as there's a force towards the center, we can go in a circle. Once there's no force towards the center, we cannot go in a circle anymore. So there always has to be a force towards the center. Okay, on to the next slide. So particle of mass m moving at speed, constant speed v, because it's uniform circular motion, around a circle, radius r must always have a net force towards the center, and the magnitude is given by mv squared over r. Okay, so what we do is going to look similar to what we've done before. In this sense, net force is ma. It's just now, it's a special kind of a, radial acceleration. And we know radial acceleration is equal to v squared over r. And then this part you have to fill in. What are the actual forces towards the center? Sometimes there's only one force towards the center. Sometimes there's a force towards the center, one away from the center. There has to be a net amount, though, towards the center. Okay? So the search for the force towards the center, that's what the rest of the chapter is really about. Okay, so the ball at the end of a string is being swung in a horizontal circle. What force is producing the centripetal acceleration of the ball? Let me try to draw this. This is a horizontal circle. I'll just say it's moving this way. There has to be some kind of force towards the center. What is it? In this case, in this horizontal circle, end of the string, it's got to be tension that's towards the center, right? That's the only force that's towards the center. There's also gravity, but that's acting straight down. Okay? Good, so tension in the string. A ball at the end of a string is being swung in a horizontal circle. What is the direction of the net force? Well, we know it's towards the center of the circle. Although the ball is going, following a circular path, its speed is this way. Oh, that's a horrible circle. Let me redo it over here. And it doesn't look like a circle because I'm trying to draw two dimensions in one dimension. Anyway, it's moving this way. This is the speed, this direction. So there doesn't have to be a force in the direction it's moving. It was already moving that way. There has to be a net force, though, towards the center to allow this to actually go in a circle. So the force is directed towards the center. Okay, great. Here's another one we can look at. An ice hockey puck is tied to a string, as you can see in the picture. Okay, to a stake in the ice. The puck is swung in a circle. What force is producing the centripetal acceleration? Okay, so centripetal acceleration means force towards the center. Same thing, it's got to be the tension in the string in this example to give us the force towards the center. I mean, there's other forces. There's the normal force on the puck from the ice. There's the weight force from the earth. Those are not making it go in a circle, though. It's the tension. If you were to cut the string, it wouldn't go in a circle anymore. It would just continue on the same direction it was going, just like the video that we just watched. Okay? So tension in the string. Here's a conceptual example. Engineers design curves on roads to be segments of circles. They also design dips and peaks to be segments of circles with radius that depends on the expected speeds and other factors. Okay, right? If you're building a highway, you wouldn't want to have a, your speed limit 75. You're not going to have any tight turns there, right? You need to have a big force towards the center then. Same thing with dips. You don't want a big dip on an expressway. Okay, so let's see here. They also design dips and peaks. Okay, a car is moving at a constant speed and goes into a dip in the road. At the very bottom of the dip is the normal force of the road on the car greater than, less than, or equal to the weight of the car. Okay, so if you're going in a circle through the dip in the picture that you see, there has to be a net force towards the center. So we're going through this path here. There has to be a net force towards the center. So the two forces that we're looking at are the normal force and the weight. So here, in order for us to have a net force towards the center, I'm going to really exaggerate this picture, the normal force has to be bigger than the weight, right? And then we actually have a net amount towards the center. Normal bigger than weight means there's a net amount towards the center. So if you happen to be sitting on a scale in your car going through this dip, the scale would actually read more than if you were just sitting on the scale not moving at all, or moving at a constant speed. So constant velocity, I should say. So if you're just going in a straight line sitting on a scale, the scale reads your true weight. If you're going through a curve here, even though the speed is constant, the velocity is not, because you're changing direction. Going in a circle means you have to have a net amount towards the center. So normal force must be bigger than the weight. And the scale would actually read more when you went through a dip like this. Okay, so that's just a synopsis of what I've said. Okay, great. Here's another conceptual example. A car is turning a corner at a constant speed, following a segment of a circle. What force provides the necessary centripetal acceleration? So it's the frictional force between the tire and the road, as you can see here. So imagine you're driving on ice and you try to turn. There's no frictional force between your tire and the ground. You can't turn. You continue to go straight. So it's static friction because your tire is not sliding out. So you're going through this path, right? And you're able to turn, and the tire doesn't slide out. By slide out, I mean go this way. So there has to be a frictional force back the other way. So it's static friction between the tires and the road that actually allow you to go in a circle. Okay, great. And that's, again, a synopsis of what I've said. Here's an example. In the track and field event known as the hammer throw, an athlete spins a heavy mass in a circle at the end of a chain. Once the mass gets moving at a good clip, the athlete lets go of the chain. The mass flies off in a parabolic arc. The winner is the one who gets the maximum distance. For male athletes, the hammer is a mass of 7.3 on the end of a 1.2 meter chain. World-class hammer thrower can get the hammer up to 29 meters per second. Pretty good. That's about 60 miles per hour. If an athlete swings the mass in a horizontal circle centered on the handle, what is the tension in the chain? Okay, let's take a look at this one. Okay, so a free body diagram would be helpful. I'm just going to do like a side view of this. So there's a tension towards the center, and this is going in a horizontal circle. So, like this. I don't know if you can tell what I'm doing. I'm up here above the paper, moving down this way into the paper, all the way back around. Okay? So it's tension that's actually towards the center. Okay, so same procedure as we had before. Net force is ma. It's just we have a special kind of a, the radial acceleration. And I know that's equal to v squared over r. And then what's the actual force towards the center? In this example, it's tension that is towards the center. Okay? I'm going to change this to force of tension. Same thing here. Force of tension. The reason I'm doing that is we have period in a lot of these problems, and I don't want to make it confusing, any more confusing than it has to be anyway. So this is force of tension. Okay? So the idea here is, here's the picture. I just have the force towards the center. I'm using Newton's second law. You're always correct when you have this part. And then what is the actual force towards the center? It's tension. And then you can solve for the tension. So in this problem, the speed was given, the radius is given, the mass is given. Put all those together and solve for the tension. Okay, let's go on to the next one. Okay, so from homework 7, this is problem 13. Well, it's the 6th one in the homework, but it's from chapter 6, number 13. Let's take a look at what we have here. So the figure is a bird's eye view, so you're looking from the sky down in this scenario, of particles on a string moving in horizontal circles on the top of a table, on a tabletop. All are moving at the same speed. Okay, so all these are moving at the same speed. You're looking down on them, they're all moving at the same speed. Rank in order from largest to smallest the tensions. So these aren't the periods, these are tensions, as it says here, tensions. Okay? So from largest to smallest. Let's take a look at this on a piece of paper. Okay, so instead of writing on a piece of paper, let me try it here with the snipping tool. So here's the 4 different scenarios that we have. We have T1, T2, T3, T4, and again, this problem is calling tension T, so I'm keeping it the same. So in general, we have this, that the tension is mv squared over r. We saw that in the previous problem. Actually, we had it written as mv squared over r is equal to the tension, but I just switched it around. Okay, so let's compare the tension for all of these. We don't want to guess, we want to base this on an actual physics. So for the first one, I can put in the specific information. So T1 from this one, okay, it's just m, as you can see, v squared, they all have the same v, and then the radius is just r. For the second one, we'll do the same kind of thing. We've got m v squared, and then this is 2r. Okay, so for the first one you can see is bigger than the second one. The third one, okay, we've got 2m, and then v squared. Again, the v is the same for all of them, divided by r. And then the fourth one, also 2m, v squared, and over 2r. Okay, so again, you'll have to go through and clean it up a little bit. For example, in the fourth one, the 2's cancel out. Actually, that's all you have to do to clean it up. And we want to rank it from largest to smallest. So, go through and see which one is actually the biggest, comparing all these to each other. It looks to me like this one's actually the biggest, right? This is 2 mv squared over r. The first one and the fourth one turn out to just be mv squared over r. And then the second one here is 1/2 mv squared over r. Okay, so the larger the mass or the smaller the radius, the bigger the tension is going to be. Okay, and that makes sense for T3 there being the largest. All right, let's take a look at the rest of the chapter 6. Okay, so here's another one. We have finding the speed on a banked turn. So you could actually go around a turn without friction if the turn is actually banked. If you ever had any kind of like Hot Wheels little track, where you send cars around curves, you can have them go around the curve really fast if the curve is banked. Sometimes in real life, going around curves, say getting off an expressway, well, you have friction towards the center, but the curve is also banked, or even in like racetracks, the curves are banked. You get an additional force towards the center when that happens. So in this example, a curve on a racetrack of radius 70 meters is banked at 15 degrees, as it says here. So we know the radius of the track, 70 meters, banked at 15 degrees. Okay, at what speed can a car make a turn without the assistance of friction? So we're not going to have any friction towards the center. We're just going to have the normal force towards the center. We'll have to have a nice free body diagram for this one. This is sort of a good start here. So here's the road surface. Here's the banked part here. So it's banked at 15 degrees. It turns out that this angle is also 15 degrees. So go through, take a look at the picture, and you'll see that this is also theta. So if this is theta, let me switch this to pen so I can draw a little bit better. I'll leave it as red. Okay, so weight straight down, there's the normal force. So if that's theta here, this is 90 degrees. You know, here to here is 90 degrees. So this angle must be 90 minus theta. And then between the x and y axis here and here, this is 90 degrees. So, and this is 90 degrees. So this one must turn out to be theta, because this is 90 minus theta. This has got to be back to big theta. Whoops, this one here. Okay, so let me just recap, just for the sake of this problem. This is theta given in the problem. We've got 90 degrees from here to here. So the angle that you see here, again, is 90 minus theta. Between the normal force and the road, it's 90 degrees. So if we have 90 minus theta there, then that's back to being theta between the normal force and the y-axis. Okay, and then the part of the normal force that's towards the center is going to allow us to actually go in a circle. Okay, so let me draw it out a little nicer than this. Okay, so here's the picture. Normal force, there, that's theta. I called this one normal x, and this one normal y, and then the weight is straight down. And we're going in this circle. So here's the circle coming, you know, kind of out of the screen like this, if you can imagine it. So use your imagination for that one. So again, we're going in a circle. Here's the radius of the circle, and we're just kind of seeing a slice of this scenario. No friction. There's got to be some force towards the center. Here, it's the normal force in the x direction that's towards the center. Okay, so it's going to take a little bit of work to do this problem, but hopefully it's not too bad. So I know from the circular motion part, the net force is ma, special kind of a though, mv squared over r. We're trying to figure out how fast we can go with this provided normal force. So the force that's towards the center is normal x. So this is perfectly good. We're trying to figure out v. The mass is not given. Sometimes if the mass is not given, you just have to keep going and hope that it cancels out. We do know the radius, and then we've got normal x, which we don't know. So we don't know v, we also really don't know m. But we don't know v, we don't know normal x. But you do know that n sine theta is equal to normal x, just from the trig here, right? The sine of theta is normal x over normal. Still can't solve it. One equation with multiple unknowns, we can't solve that. We've run into this situation before. We've got to get more equations. So let me look at what I'm calling the y direction. And in the y direction, I know that the weight has to be equal to normal y. The weight is mg, and the normal y from the picture is n cosine theta. Okay? So there's several ways of solving this. I'm just going to do it like this. Mg is equal to normal y. This is n cosine theta. So what you could do, I'll just say it, solve for the normal force here. So that would be mg over the cosine theta is the normal force. Solve for the normal force here, and then plug it in here. And then you'll see that it cleans up nicely for you. Now, if you take this and plug it in for the normal force, you don't need to know the normal force anymore. You do know theta. The m would cancel out. You would be fine that way. I'm just looking at this part and this part. And I'm only doing this because it's a cleaner way to do it mathematically, but it doesn't matter. I'm going to divide the left-hand side and the right-hand side. So if I do that, mv squared over r divided by mg, the m's cancel out, and I'm left with v squared over rg, and on the right hand side the normal force cancels out. Here the mass canceled out, and then over here on the right hand side, normal over normal, that becomes 1. Sine over cosine is the tangent of theta. And then I have what I want. V squared over rg is the tangent of theta, so v then is the square root rg tangent of theta. Okay? I've multiplied both sides by RG, took the square root. And that's how you can solve for how fast you can go. So the bigger and bigger theta is, the more inclined the track is, the bigger the angle, the faster you can go. Now, if theta is 0, there's no speed that you can turn without friction. Okay, so the more and more you bank it, the faster and faster you can go. Okay, let's move on. Okay, so centrifugal force. This is the force that doesn't really exist, but it seems like it exists to you. So if you're a passenger in a car that turns quickly, it is the force of the car door pushing on you that keeps you going in a circle. But it feels to you like you're being thrown out of the car, right? If you're going around a turn, say there's no door on the car, it feels like you're being thrown out of the car. You're not really being thrown out of the car. You would normally just go that way anyway. There has to be some force towards the center that allows you to turn in the first place, and it's the normal force from the door on you that's towards the center. So no force towards the center, you can't make a turn. Usually, I mean, you don't have to lean in the door. There's static friction between you and the seat. There's got to be some force, though, that's towards the center that allows you to go in a circle. Now, if there's not, and there's no door, there's not a lot of friction, it feels to you like you're being thrown out of the car, which you're not really being thrown out of the car. You would go that way normally, just like the video we saw earlier. Okay, there's a little bit about apparent weight in circular motion. So remember, apparent weight just means the normal force that you feel. Okay, so we can do the free body diagram up here, the free body diagram down here, and look at how much the normal force is. So it turns out down here at the bottom, the normal force is greater than the weight. And up here, we'll have to figure out how they're actually related to each other. So the bottom picture, this is kind of like the same thing we did with the car going through the dip in the road. The normal force has to be bigger than the weight for us to have a net force towards the center. Up here, they're actually both towards the center, so we don't know which one is larger, which one's smaller. We just know that in this top one, if you looked at the normal force for somebody stationary versus the normal force of somebody moving in a circle, you're going to feel lighter up here at the top. So you'll feel lighter. If you were sitting on a scale, the scale would read less. Okay? All right, let's go on from here. So the force you feel, your apparent weight, is the magnitude of the contact force. So the apparent weight, again, that is the normal force, what the scale would read. Okay? Good. So when the passenger on the roller coaster is at the bottom, the normal force is bigger than the weight. Okay, so don't let the word apparent weight scare you. It just means, what would the scale actually read? Okay, so here's one that we can take a look at. A handful of professional skaters have taken a skateboard through an inverted loop in a full pipe. So they're basically going upside down, and they can make it all the way around if they're going fast enough. So a typical pipe, 14 feet diameter, what is the minimum speed the skater must have at the top of the loop? Okay, so we need a picture for this one. We just do the free body diagram at the top. So we're in contact with the top, and we also have the weight here. They're both towards the center. So the diameter is 14 feet. 14 feet's about 4.2672 meters. We really want the radius, so we'll have to cut that in half. Here. Actually, I got my calculator handy. 4.2672 divided by 2. So 2.1336. 2.1336 meters. Okay, so that's the radius. So we start these problems like this. F is equal to ma, special kind of a, that's why I'm putting a little r there. This is equal to mv squared over r. And then what are the forces towards the center? Well, in this problem we have the normal force and the weight. Okay, so they're both towards the center. So when it says here, what is the minimum speed the skater must have at the very top? So pretend that you're actually doing this. You go really fast, you make it around really easily. You start going slower and slower and slower. Eventually you get to the point where you don't go in a circle anymore. At the top of the loop, you just fall down. So falling down means the normal force is equal to 0. You're not in contact anymore. So let's do the case where the normal force is actually equal to 0. That means you're not in contact anymore. And then realize that we actually have to go a little bit faster than that because we want to have the normal force be greater than 0. If the normal force is 0, that means you're not in contact anymore. We're going to solve it for not being in contact anymore, and then we have to go faster than that. So that's why I'm setting the normal force equal to 0, and then again I'm saying I have got to go a little bit faster than that. If you were a professional skater, you probably wouldn't want to push your luck, right? You'd want to go as fast as you can. So let me again do normal force equal to 0. So I've got mv squared over r. Normal force 0, so the weight is equal to mg. And then, the mass wasn't given, it actually cancels out. So v squared is equal to rg. And then you can solve for how fast you need to go. I won't put the numbers in here. You have everything, you can plug it in there. Okay, let's take a look at problem 6.24 from the homework. Okay, so the passenger in a roller coaster feel 50% heavier than their true weight as the car goes through a dip. Okay, so they're saying the normal force is 50% more than it usually is. And then if you want, you can take a look at this video tutor solution from the author of the book. What is the car's speed at the bottom of the dip? Okay, so the normal force is 50% more than it usually is. How fast are we going through this 40-meter dip? And if you notice, the mass is not given, but hopefully it's going to cancel out. Okay, let's take a look at this. Okay, so here's the picture. We're going through a dip in the road like this. Here's the normal force, and here's the weight. And again, I drew the normal force larger than the weight to give us a net force towards the center. The radius of this path is 40 meters. What is the speed if the normal force is 50% more than it usually is? So they're saying that the normal force is 50% more than it usually is. So the normal force is 1.5 times mg. Right? That would make it 50% more. If you want, how did I get that? You can think of it like this. Normal force is equal to mg plus half more. So that would make it 50% more. And then you get 1.5 mg. So usually it's mg, but it's 50% more. So let me add 0.5 mg to that. That would be 50%. Okay, so this is the key point for this problem. The free body diagram is really important as well. As you can see here, we've seen this already a few times today. And then the problem starts the same way. Net force, MA, special kind of A, towards the center. That's equal to mv squared over r. And then it's up to us, again, to supply the forces towards the center. To have a net amount, the normal force is bigger than mg. Okay, so that's perfectly good. Right now, I'm going to have to use this little extra bit of information that I had before, put that in there for the normal force. So we've got mv squared over r, 1.5 mg, that's the normal force. They tell us that in the problem, and then minus mg. And then there's an m in each term, so the m's cancel out. Okay, divide out however you want to think about it. So v squared over r, 1.5 g minus a g gives me 0.5 g. Then you can solve for the speed. V is the square root of 0.5 rg. Okay, good. And when you get that speed, it says minimum, but really you want to go faster than that. Okay, let's continue. Okay, so a physics textbook swings back and forth as a pendulum. Which is the correct free body diagram when the book is at the bottom and moving to the right? Okay, so there's no kind of like horizontal force that we have to look at, right? It's already swinging. So D and E don't work because there's nothing there. It's already moving. It's got momentum that way. At the bottom of the swing, we know that there has to be a net force towards the center. And anywhere there has to be a net force towards the center if it's going in a circle. So C is the only one that actually has a net force that's towards the center. Okay, very good. We'll do a few more of these. A car that's out of gas coasts over the top of a hill at a steady speed of 20. Doesn't really matter that it's 20. The fact that it's steady is the key here. Assume air resistance is negligible. Which free body diagram represents describes the car at this instant? Same thing. There doesn't have to be any kind of force that's moving it forward. It already has some kind of momentum. Remember, it's out of gas. It's just coasting. So let's look at the free body diagram at the top. There has to be a net force that's towards the center. So there's the radius. So in order for there to be a net force towards the center, the weight here has to be bigger than the normal force. It's the opposite of the one that we just did with the roller coaster in the dip. Good, so whatever one corresponds to this picture at the top. Let's see. This one. Good. So you can see that the weight is bigger than the normal force. Okay? That gives you a net amount towards the center. Okay? Roller coaster does a loop-the-loop. Which of the free body diagrams shows the forces on the car at the top of the loop? Okay, so we're upside down. So here we've got both the normal force and the weight that's towards the center. Okay, same thing. There's no kind of force moving it forward. It was already moving that way to begin with. So they're both towards the center in this example. Okay, great. The track is above the car, so the normal force pushes down. Here's an example problem. A car of mass 1,500 kilograms goes over the hill at 20 meters per second. The shape of the hill is approximately circular, radius of 60. When the car is at the highest point, what is the force of gravity on the car? And then what is the normal force? Okay, so the force of gravity, that's the weight. That's still just equal to mg. So you can solve for that, right? The mass is given. G is 9.8. This is the force of gravity. Force of gravity, weight, same exact thing. Okay, so you can do that. What's the normal force on the car at this point? Okay, so in terms of the free body diagram, I'll write it up here. Whoops. Here's the normal force. Here's the weight. So the weight is bigger than the normal force. That gives us a net force towards the center. So the procedure here, circular motion, this is all that we have. MA, special kind of A called radial acceleration. I know that that's v squared over r. And then it's up to us to supply the details here. Now in this one, I'm writing weight minus normal force. So in order for there to be a net force towards the center, the weight has to be bigger than the normal force. We'll have to do a little bit of algebra then, and then we can solve for the normal force. I'll have to write it here at the top of the screen. So mv squared over r, weight minus normal force. Let me move the normal force to the left-hand side of the equation and mv squared over to the right-hand side of the equation. And when I do that, I get this. Normal force is equal to the weight minus mv squared over r. Whoops. Okay. So again, we have everything that we need. The speed's given, the radius is given. You can solve for the weight in part A. Now notice, if you're not moving anymore, this is a v squared, by the way. Hopefully you can read my writing. That's v squared. So we have the weight minus mv squared over r. When v is 0, the normal force is just equal to the weight. When you're moving, the normal force changes. Right? The faster and faster you move, the smaller and smaller the normal force becomes. That's why when you go over a bump in the road like this, you actually kind of sometimes maybe even come out of your seat, or you feel a little bit lighter, that sort of thing. If you were sitting on a scale, the scale would read less than if you were just sitting on the scale and not moving in this situation. Okay, let's look at the next one. Okay, so circular orbits and weightlessness. So we're always experiencing this, believe it or not. We're on the Earth going around the sun, so we're going in a circle. There's got to be a force, on the Earth from the sun that allows us to go in a circle, and that's the force of gravity between the sun and the Earth. The moon going around the Earth, the same thing. Satellites going around the Earth, the same thing. So if you've got your cell phone, you are utilizing this whole idea. So orbital motion, So you know, if you have a projectile moving, it's falling towards the Earth. The force of gravity is towards it. But what if you're going fast enough that as you fall towards the Earth, you move? Let me draw this on here. So as you're falling towards the Earth, this way, for example, you're also moving this direction, falling towards the Earth, moving this way. If you're going fast enough, even though you're falling towards the Earth, you're moving off to the side. That's what orbiting the Earth actually means. So the force of gravity on a projectile is directed towards the center of the Earth. But say you move fast enough this way or this way, if you move fast enough, you're not going to hit the Earth. You're going to be able to orbit the Earth. That's what orbital motion actually is. So it's that weight force towards the center that that provides the force towards the center. So if the launch speed of a projectile is sufficiently large, there comes a point at which the curve of the trajectory and the curve of the Earth are parallel to each other. And then you can see in this better picture that you're actually in an orbit. So an orbiting projectile is in free fall. So again, what does free fall mean? Under the influence of gravity. So it's that force that's towards the center. Okay, so we know F is equal to ma, so A is F over m. So what is the force towards the center? Well, we just said it's the weight here. You could put in mg for the weight, and it turn out to be that the acceleration towards the center just turns out to be g. Now this is okay if you're close to the surface of the Earth. When you get away from the surface of the Earth, though, g is not constant. It's just we use 9.8 close to the surface of the Earth. So an object moving in a circle of radius r at speed v will have a centripetal acceleration, as you saw above. This radial acceleration, centripetal acceleration, turns out to be g, and then we can put in v squared over r. Again, this is only good if you're close to the surface of the Earth. So the orbital speed would have to be g times r, solving for v in this equation. Solve for orbital v, and you get this. Again, that's only kind of an approximation, only works close to the surface of the Earth. Okay, so orbital speed skimming the surface turns out to be g times the radius of the Earth. So the radius of the Earth, you can look it up in the chapter or the front of the book, 6.37 times 10 to the 6th meters. So you got to go about 7,900 meters per second, or about 18,000 miles per hour. Okay, you can also calculate the speed of this orbit. So remember the orbital speed, let's call it VO, distance around, 2 pi r, and then divided by the amount of time it takes to get around. So then you can solve for the amount of time, and that's where this is coming from. So good, and then put everything in, put the orbital speed in, put this equation in here. There's a step of algebra that's not shown here. You get the period to be 2 pi square root of r over g. Okay? So these formulas I never remember. I have to always go back to just the fundamental idea, this idea here. Okay? Good. And then we can put in what we had up here. So as you're constructing your formula sheet for the next test, if you put this on here, make sure you know where it comes from. And make sure that you know this is period, not tension. So astronauts and their spacecraft are in free fall. It's just they're going fast enough that they don't hit the Earth. Right? They're flying towards the Earth, but then they're moving off to the side, just like you saw before. Okay, looks like a lot of fun. So the moon, like satellites, is simply falling around the Earth. So if you use the distance to the moon, and you tried to use the g at the surface of the Earth, you don't get a very good number. You get a period of 11 hours. And it takes the moon a month to go around the Earth, not 11 hours. So there's something wrong with this formula. And what's wrong with it is it's only good at the surface of the Earth. Okay? So it's more complicated than that. Works okay at the surface of the Earth, but we'll have to come up with a better formula in general. Okay, here's an example. And this is similar to 6.32 on the homework. Phobos is one of the 2 small moons that orbit Mars. Phobos is a very small moon, surprisingly small gravity. It varies, but typically it's 6 millimeters per second squared. Okay, so be careful, that's not in SI units. Isn't quite round, but has an average radius of about 11 kilometers. What would be the orbital speed around Phobos, assuming it's round and the radius is as noted? Okay, so we can put all this information together and assume that we're going, close to the surface of Phobos. I'm assuming that's what the 6 millimeters is. Okay, so let's actually do this one. So the g of Phobos, 6 times 10 to the minus 3 meters per second squared. That's what the g of Phobos is. And then when the average radius is of 11 kilometers, so 11 times 10 to the third meters. Take the square root of that. So basically we're taking the square root of 66, right? Because 10 to the minus third times 10 to the positive third becomes 1. So the square root of 66. Whoops. How much is that? Let me use my calculator. 66 raised to the 0.5 power. So about 8.12 meters per second. So approximately 15 miles per hour. So, I mean, I could do that with the baseball. I could put a baseball into orbit around Phobos. Take a baseball, throw it at least 15 miles per hour, and it'll be in orbit around Phobos. Okay? Excellent. So that's similar to 6.32 on the homework. I think this number is pretty neat, so I wanted to put the numbers in for that one. Okay? Excellent. Let's move on to the next part. So Newton's law of gravity. So anything with mass is attracted to anything else with mass. It's one of the fundamental laws of force laws of physics. So gravity is a universal force that affects all objects in the universe. Anything that has mass is attracted to anything else that has mass. The thing is, it's unless the masses are really big, you don't feel it. The mass of the Earth is big to us, so we feel that force. If you just had an eraser next to another eraser, they're not going to suddenly move towards each other because their masses are not very big. So it's directly proportional to the amount of mass you have and inversely proportional to the distance between them squared. Okay, so if you're twice as far apart, the force is 1/4 as much. So Newton came up with this. And here's the formula. The force 1 on 2 is equal to the force on 2 on 1. So say it's between me and an eraser. There's a force on the eraser from me. There's a force on the eraser from me. Back and forth. It's both of those. We're both attracted to each other gravitationally with the same force. Now this is big G. So big G is 6.67 times 10 to the minus 11th newtons meters squared per kilogram squared. So it says here, let's find little g. So let me show you where this little g that we had before, this 9.8, actually comes from. Okay, so here's the Earth. So ME means mass of the Earth, and then here's me over here on the surface of the Earth, and I'm just giving myself mass of little m. And then the distance between the center of the Earth and me is the radius of the Earth. So I could use Newton's law, gravitational force law, to figure out the force on me from the Earth. That's what the weight really is, the force of gravity. So we know it's big G times mass of the Earth times my mass, and then the distance between us squared. Right? You saw it like this. M1, M2, distance between us squared. Well, this is the mass of the Earth. That's playing the role of M1. My mass, that's mass 2. Again, I'm just looking at the force between me and the Earth. And then the distance between us, if I'm on the surface of the Earth, is the radius of the Earth. So I could do this every time to figure out the force of attraction between us. The thing is, if I'm on the surface of the Earth, the part here that I circled is not going to change. I don't want to have to punch it into my calculator every time. So let's actually see what G times mass of the Earth times radius divided by the radius of the Earth squared turns out to be. So we've got 6.67 to the minus 11th newtons meters squared per kilogram squared, and then times the mass of the Earth, 5.98 times 10 to the 24th in kilograms, and then divided by the radius of the Earth. We actually saw this number earlier today. 6.37 times 10 to the 6th meters, and then don't forget to square it. Now, if you put this in your calculator, actually let's look at the units too. So meter squared, that cancels out. Kilogram squared and kilograms, one of those cancels out. So we've got a Newton per kilogram. So a Newton is a kilogram meter per second squared, and then I'm dividing it by kilograms. So this turns out to be meters per second squared. Let's actually see what we get. 6.67 EE minus 11th times, 6.67 to the minus 11th times 5.98 to the 24th divided by 6.37 to the 6th. Don't forget to square it. 9.8. So we've been really doing this the whole semester. We just called this little g before. So everything I've got circled up here, this is little g when you're on the surface of the Earth. That's what this whole thing is. So we have been using Newton's universal gravitational force law the whole semester, but why re-put everything in? The mass of the Earth isn't changing much. The radius of the Earth, we're just assuming it's not changing either for where we're at. So we have been doing this the whole time. Okay? Pretty cool. So you don't have to punch this in every time. But if you're not at the radius of the Earth, if you're, say, a satellite going around the Earth, where you're not exactly, at the radius of the Earth, this is going to be bigger. So then the force of gravity between you is going to be smaller. Okay? I just use radius of the Earth in the formula here, but what if you're farther away from the surface of the Earth? Then the force is going to be less. Okay, let's keep going. Okay, so let's actually use Newton's universal gravitational force law to solve this one. The centers of a 9 kilogram lead ball and a 100 gram, okay, be careful, 100 gram, change that to kilograms, are separated by 15 centimeters. What gravitational force does each exert on the other? Okay, good. So we're given both masses, the separation we're given. We know big G is just a constant. We want to figure out the force of attraction between those two. Okay, let's take a look at it. Okay, so here's the formula we have. G m1, m2 divided by the distance between them squared. So here's mass 1, here's mass 2, here's the distance between them. Don't forget big G is just a constant, 6.67 to the minus 11th. So it's a really small constant. Newtons, meters squared, kilograms squared. So you have everything, just put it in the formula here. You're going to see it's a really small force, right? Because big G is to the minus 11th. You're going to get a small number here, which you would expect to. You see everyday items like this don't suddenly start flying towards each other. There is a force between them, it's just really, really small. So that's the first part. You can just put all the numbers in to the formula here. The second part is to take the force that you found from the first part and divide it by the weight of the 100 gram ball. So, take whatever you got from the first part, this is for part B, and divide it by the weight of that ball. So this would be mass 2 times G. The part B is to show you really how small this force is in relation to the force of gravity on the 0.1 kilogram mass. Like the force of gravity is the Earth force on this. The force from the Earth is so much greater. This is going to be a really small number. You might actually have to put your calculator into scientific notation to get enough digits to solve this. Okay? Because it might be really small compared to that. Okay, so just keep that in mind. Okay. Okay, so I've already kind of alluded to it. You have one object going around another object, like the Earth going around the Sun. It's the force of gravity from Newton's universal gravitational force law that provides the force towards the center of that circle. Okay, so I'll just read it here. Newton's second law tells us the force of big M on little m, so whatever is being orbited they're calling big M, and whatever is doing the orbiting is little m, is equal to ma, where this is the universal gravitational force law. Okay, so really it's going to be the same procedures that we've done. We're looking for the force towards the center. It's just the force towards the center here is the force of gravity. Okay, so I guess I would write it like this actually. What we have here is good. It's just kind of written backwards. I would do it like this. F M A, special kind of A, radial acceleration. So this would give us mv squared over r. Then I would ask myself, well, what is that force? Well, it's the force of gravity, which I know is big G, one of the masses, the big mass, the little mass, and then the distance between them squared. So logically, I would think of it like this. The net force, ma, mv squared over r. Then what is the actual force towards the center? It's this one. It's the gravitational force. Big G, mass of one of them, mass of the other one, and then the distance between them squared. Again, what you have here is good. It's just, to me, written backwards. We should have started here and maybe moved that way. Okay, just to keep everything consistent with what we have been doing. So you can clean this up a little bit. If you notice, each of these terms here has a little m in it, so the little m cancels out. There's an r on the left-hand side and r squared, so this cancels with one of those. And then you can solve for v. That's what's being done. So solve for v, basically take the square root of both sides after doing what I've done with canceling out the m and one of the r's from each side. Take the square root, and you get this. So this is the orbital speed. Okay, and this is more general, right? There's no little g or anything like that. This is big G and r. So a satellite must have this specific speed to maintain a circular orbit of that radius. Okay, so probably on your formula sheet, get a little orbital motion, satellite motion section going. Maybe even have this picture. This is a nice picture here. Here's the formula for the speed. Okay, so big G, big M. The big M again means whatever's being orbited, the bigger mass, and then r is the distance between the big mass and the little mass. Okay, and you could also use the relationship that the speed is 2 pi r divided by the period, and plug that back into the previous formula that you saw. So big G, big M over r, the square root of that has to be equal to 2 pi r over the period. That's where this is coming from here. Okay, so you can solve this several different ways. Here, basically, they've put the period on one side and the radius on the other side. Did a little bit of algebra. So the period turns out to be 4 pi squared over big G times big M times r cubed. So this is another good one to have. I mean, all of these are really. I mean, this is good as well. So this is something that makes up one of Kepler's laws. So if you know anything about astronomy, you might have heard of Kepler. He's got 3 laws. This is one of them, where the period is proportional to the radius cubed. So the period squared, I should say, is proportional to the radius cubed. So this is one of Kepler's laws. Okay. Okay, excellent. So we got the speed, we've got how the period's related to the orbital distance and that sort of thing. So let's take a look at 6.49 instead of doing this problem. Okay, so the International Space Station is in a 280-mile high orbit. So that's the distance above the surface of the Earth. What is the station's orbital speed, given the radius and the mass? And then part B is, what is the station's orbital period? Okay, let's take in minutes. So you might think that this gives you a clue. It's in minutes here. Oh, is it a lot of minutes? A little bit of minutes? You might think, the space station going around the Earth would take days or so. I mean, what's your best guess? It's hard to even say. Don't be surprised if it's actually in minutes. It's hard to really fathom that you can go around the Earth that quickly. But this is just going to be in minutes. So not a lot of minutes either. Maybe hours would be a better measurement, but minutes still works here. Okay, so let's take a look at the picture of this, and they also give us the radius of the Earth and the mass. Be careful, this is in miles here. You'll have to convert that into meters. Okay, let's take a look at this. Okay, so here's the picture. Here's the Earth. Here's the space station here. A certain height above the Earth. So this is not drawn to scale at all. So they tell you the height above the Earth is 280 miles. You'll have to change that into meters. I'll let you do that. Convert that to meters. The radius of the Earth, 6.37 times 10 to the 6th. And then h is the height above the Earth. It's not drawn to scale. And in Newton's law of force law, the distance is between the center of the Earth and where the object is located. So you'll have to take the radius of the Earth and then add 280 miles in SI units to that to get the distance away. Okay, and then the speed turns out to be big G. This is again the mass of the Earth because that's what's being orbited, and then divided by r. So you'll have to come up with r, and then the mass of the Earth is actually given too. Let's see, I believe it's 5.98 times 10 to the 24th kilograms. Okay, so put that all together. Big G is that constant that you saw before. Mass of the Earth, that's just a constant also. This r is what you have to come up with. Take the radius of the Earth, add it to 280 miles once you convert 280 into meters. That's how you can get the speed. A couple different ways of getting the period. You could use that longer formula where the period squared was proportional to the radius cubed. Or if you get the speed this way, the speed is 2 pi r divided by the period. So the period is going to be 2 pi r over the period. And it's the same thing, over the speed. And this r is the same thing that you got up here, the total distance from the center to where the International Space Station is at. So the speed here will come out in meters per second. So then the period is going to come out in seconds. You'll have to convert that to minutes. Okay? Have some fun with it, and we'll talk about it more next time we meet. Okay? Bye-bye.